Welcome to the week 3 lectures on this topology course. In the last couple of weeks, we have seen some set theory and logic, and in the last week itself, recall that in the last week's lectures, we saw the definition of topology. Then we saw 3 ways to define topology on a set X. Define a topology on a set X. So the first way was simply to define a topology by describing directly the open sets, describing explicitly the open sets in X. So giving a direct description of the topology on X. The second way we saw was to give a basis on X which generates a topology. And the third way was to give a sub-basis, which again which gives a basis, and this gives a topology. So these were the 3 ways in which we have learned how to define a topology. So in this week, we will see various different kinds of topology on a given set X, and we start with the so-called subspace topology. Subspace topology, and this is about a subset of a topological space. So suppose that X and X is a non-empty set and tau is a topology on X. So this is a topological space, and suppose that a Y is a subset of X. Then the subspace topology gives a way to define a topology on Y. So we have a topology on X, and Y is a subset of X, and the subspace topology gives a way to define a topology on this subset Y. So how do we define this? So definition of the subspace topology. This is simply given by this following collection of subsets of Y. So define a topology which we denote by tau Y on Y as follows. So tau Y is the following collection. This is the collection of intersections U intersection Y for U, an open set in X. So remember that tau was a topology on X. So an open set in X is in tau by definition, and we take the intersection of these open sets with the set Y that we have. Okay, and this is our claim is that tau Y is a topology. So when I say when I gave the definition, I already claimed that it is a topology, and let's try to see why it is a topology. So proof. So first of all, see that the empty set and Y. So we have to show that the empty set and Y are in tau Y. This was the first axiom of topology. So why is the empty set in tau Y? So of course the empty set, since the empty set belongs to tau, we can consider phi intersection y, and we know that the intersection of any set with the empty set is the empty set itself, and so this is in the collection tau y, okay, because we are taking intersections of empty sets of open sets in X in tau with the set Y. So the empty set belongs to tau Y. Similarly, since X belongs to tau, we have Y as it can be written as Y intersection X, since Y is a subset of X, so Y is just Y intersection X, and this is then of the form that we want as a member of this collection tau Y, and so this belongs to tau Y. So the empty set and Y belong to tau Y. Now we need to check that arbitrary unions and finite intersections are in tau Y. So for arbitrary unions, so suppose that U alpha alpha in J is a collection, is a family of index subsets, a family of open sets indexed by J, is a collection of open set in Y, or in tau Y, indexed by J, then we need to show that the union of all these sets U alpha belong to tau Y. So to prove this, note that each U alpha is of the form, so note that each U alpha is of the form V alpha intersection Y, where V alpha belongs to tau, which is an open set in X. So then we have the union of these sets of these sets U alpha is nothing but the union of V alpha intersection Y alpha in J, and now we use the distributive property of intersections and unions, and then this gives us the union over V alpha intersection with Y. So using the distributive law of intersections and unions. So what is the distributive law? It just says that a intersection, any union, so let's write something like this: any arbitrary union over an indexed set J, this is equal to the union over the index set J and the individual intersections of A with these B alphas. Okay, so this is the one of the distributive laws. You can also have the distributive law of union over the intersection, so you interchange the roles of intersection and union here, and you have a similar law. So in our case, we have written the arbitrary union U alphas as a union of V alphas, where V alpha, remember, is open in tau for each alpha, and now this belongs to tau because arbitrary unions of open sets are in tau. So then again, this is of the form that we want. It is an intersection of an open set in tau and Y. So this is, therefore this belongs to tau Y. And similarly, one can do the finite intersection property, finite intersections. So if u1, u2, un are in tau y, then the intersection I equal to 1 to n of ui, this should be in tau y. So we want to show that this is in tau y. So why is this so? This is because again each ui is equal to some vi intersection y, where vi is an open set in X, is in tau. So this means that the intersection of these finite intersection of these ui's, this is nothing but the intersection of vi intersection y. And so here let me write, this implies that ui equals this intersection, and then again this is nothing but the intersection of vi, I equal to 1 to n intersection y, and this is nothing but the associative property, associative law of intersections. Okay, so if you have just 3 sets, for example, then A intersection B intersection C is the same as A intersection B intersection C. So you can generalize this for finitely many or even arbitrarily many sets and take the intersection one by one, and you will have this result here, this equality here. So then again we have written ui in terms of an open set. Remember that each vi is open in tau and we are taking finite intersections, so this belongs to tau, and then we have the intersection with y, so this implies that ui is in tau y. So we have shown that tau y is a topology, on y. Now I'll just fix a notation. So if y is a subset of x and x has some topology, so x tau is a topological space, then if y is given the subspace topology tau y coming from tau, then we write y with a triangle pointing towards the left, y, and then we write x on the right. Okay, so we will remove the remove the topologies tau and tau y from the notation whenever it is clear which topologies are we talking about. So for just as a shorthand we will use this notation. Now let me give another lemma. So this lemma says that if B is a basis on X for a topology tau, then the collection BY, which is defined as the collection of intersections of elements in B with Y. Okay, so B is coming from this basis on B on X, and you take the intersection with Y. Then this is a basis on Y which generates the subspace topology tau y. So the proof is quite simple. So we just have to check that first of all that this is a basis, and then the topology it generates is exactly tau of y. So let's see a quick proof. So let us start by proving that by is a basis. So we have to check the two properties for a basis. The first one was to show that if y is in y, then there exists by in this collection by such that y belongs to this set. So what is by? Of course, if y is in y, because because b is a basis for x. So now, first of all, if y belongs to y, then y is in x, of course, because y is a subset of x. And so this implies that there exists a basis element b in the basis for x, such that y belongs to b also. So then this means that y belongs to b intersection y, and this is our by that we need. Okay, so y belongs to this set by, which is just the intersection of the element b in the basis for x and intersection with y. So the first property is simple. The second property is to show that if y belongs to b1 y intersection b2 y, so here b1 y and b2 y are in this collection by, then there exists a b3 y which belongs to this collection by, such that y is in b3 y, and which is a subset of b1 y intersection b2 y. Now note that b1 y is of the form b1 intersection y for b1 in this basis b for x, and similarly b2 y is also of the form b2 intersection y for some b2 in the basis for x. And so if y is in the intersection b1 y intersection b2 y, this means that y belongs to b1 intersection y intersection b2 intersection y, and this is nothing but b1 intersection b2 intersection y. Okay, so you can switch around the sets here, and then you will have b1 intersection b2 and then y intersection y, which is just y. So it is b1 intersection b2 intersection y, and then this means that y belongs to b1 intersection b2 first of all, and y is in y. And because these are basis sets, this means that there exists a b3, okay, in the basis b for x, such that y belongs to b3 and it is a subset of b1 intersection b2. Okay, and we also have y is in y. Okay, but this means that y belongs to b3 intersection y, and it is a subset of b1 intersection y intersection b2 intersection y. Okay, so we just take the intersection with y on both sides here, and we get this. So this is our needed this basis element in by that we require, and so we have shown that by is a basis. Now we still need to show that by generates tau y. And for this we will use the theorem that we proved earlier. So we will use theorem 6.1 in week 2's lecture 6. Okay, and this just gave a way to determine whether a basis generates a topology tau of given a topology, whether a collection of sets is a basis that generates that topology. Okay, so please check this out again. Check what this theorem said and how we can use it to show that by generates tau y. So in fact, it suffices, it is enough to show that given any open set in tau y, say u, there exists a by in the basis by over y, such that okay, so you take a point here y, okay, then there exists a basis by such that y is in by and it is a subset of u. Okay, so if you look at the theorem 6.1, this exactly means that by intersection with this collection of y u. So let me write uy to distinguish open sets in X from open sets in Y. Okay, so yuy is non-empty for any ordered pair of point and an open set that contains the point. Right. So what was yuy? This was, if you check the definition, this is nothing but the open sets in tau y such that y belongs to V. Again, let me write Vy just to distinguish it from the open sets in Y. And Y is in this open set to Vy, and it is a subset of the open set Uy. Okay, so here Uy is again in tau y. And so if you have this basis set, so if a collection B satisfies such a thing, then it generates the topology that you use to take these ordered pairs, right? So it is sufficient to find a basis set by in this collection by such that y is contained in this basis set, and this basis set is then contained in this open set uy. So why is this true? So to show this, note that uy itself is of the form u intersection y for some u in the topology tau on X, right? This is how we define it. And so what should be our B? Well, we have that B is a basis for tau. So this means that y is contained in some basis element B, and this basis element is a subset of U. Okay, so now we just take the intersection of this set B with y, and we're done. So this means that y belongs to B intersection y, and this is a subset of U intersection y. And so this is our required by, and of course this was our uy, and this is what we wanted to show. So this means that by is a basis for the topology tau y. So now let me give a couple of examples of subspace topologies. So the first one is that if X is given the discrete topology, then we know that the basis for the discrete topology, as we have seen, so then B, which is just the one point sets of elements of X, this is a basis for the discrete topology. So then if Y is a subset of X, then the basis for Y for for the subspace topology on Y is nothing but these sets X intersection with Y, where X is in X. This is how we define the basis. But this is nothing but the singleton sets Y, where Y is in Y. Why is this? Because, well, if X belongs to Y, then this set, the singleton set X with intersection with Y, is nothing but the singleton set X itself. And if X does not belong to Y, then the intersection is empty, is the empty set. So we add the empty set as well in this collection BY. Okay, and this is a basis for tau Y, and this is nothing but the discrete topology on Y. Okay, so the subspace topology on Y is nothing but the discrete topology on Y. Now another example is if you take X equal to the real line, and let's say Y is the interval 0, 1 closed, okay, in X, and we take the standard topology on the real line R, right? So the subspace topology on Y is given by the collection. So first of all, you will have all the open sets, open intervals A, B. Okay, so let me write it as a basis. So they're given by the basis. So we know that the basis for the standard topology is given by these open sets, right? So then we need to take these intersections with the basis sets A intersection B, AB in the real line. And so what is this collection? So you have the real line, and you have 0, 1 here, and so the interval AB can lie either like this, okay, it can lie entirely within this interval, or it could also lie like this, or it could also lie something like this, A, B, completely encompassing the interval 0, 1. So in all these cases, you will notice that the basis BY, it is the collection of sets of these following forms. So either you have 0B with B less than 1, then you have A1 closed, so A at the endpoint A it should be open, A1, so A greater than 0, and of course here 0 is greater than B, B is greater than 0, and here A is less than 1. And you can also have AB where 0 is less than A is less than B is less than 1, so elements of this form where the interval AB completely lies inside the interval 0, 1. And finally you have the set 0, 1 itself, because if you take a large open interval which contains 0, 1, then you will get this this set 0, 1 itself. Okay, so all these are the basis sets, okay, for this subspace topology BY. Notice that there are some more open sets than the usual, because in general, note that 0, 1 or 0B or A1 is not open in R, so with the standard topology, right? Because if you, for example, for this one, if you take the point 0, then there is no basis element that contains 0, and it is contained in this half closed or half open interval 0b, as we have seen for the lower limit topology. So it's not open in the standard topology in R, but these are open in the subspace topology for Y. So there are some more open sets than usual, and we have to keep this in mind whenever we use the subspace topology. So we will finish our discussion of the subspace topology here, and we move on to some other topologies in the next lecture.